Hey everyone, and welcome to section 7.4. As promised, we're going to be talking about solving rational equations. If you didn't already guess this by now, equation is an equation that involves rational expressions. So here's an example. Now, if we take the equation and we find a common denominator, which in this case would be 6x, we can multiply both sides of the equation by 6x. We are left with 6 plus 2x equals 5x. We can solve that no problem. 2 equals x. So that's not so bad. Alright, we want to solve the equation if we can. I think we can rise to the challenge. So again, we want to multiply by a common denominator. In this case, a y squared would work. So if we multiply both sides of the equation by y squared, we would get y squared minus 5y squared over y equals negative 6. And this simplifies. After simplifying, I moved the 6 over from the right-hand side to the left-hand side. This is now a quadratic equation, which we can easily solve. So our solutions are 2 and 3. When we're solving rational equations, though, we want to be careful. We want to make sure that we're not doing anything to introduce extra solutions. So you can have this thing called an extraneous solution, which is any solution that the original equation is not defined at. Okay, so we want to multiply here by a common denominator. We know that the expression on the right-hand side factors nicely. So this is a good common denominator. Let's multiply by that. Okay, and lots of stuff's going to divide out. So we get that x is equal to negative 1. Then we just got to check, is this solution defined? So is the original equation defined when we input this solution? And yeah, the only thing that's going to cause division by 0 would be 2 or negative 2. So that's all good. All right, another equation. Let's remember, usually it's a good idea to factor things as much as possible when we're working with rational expressions. So this first guy, I know the denominator has a common factor of 2. And the second fraction, the denominator has a common factor of 3. And on the right-hand side, the fraction has a denominator that has a common factor of 12. And then we end up with x squared minus 1, which actually, you know what, let's rewrite that now. Okay, now we got to multiply by a common denominator. What we have on the right-hand side is going to work. All right, and again, lots of stuff's going to drop out, so that's nice. And while it's not ideal, we don't have rational expressions anymore. We just have regular old polynomials, which is a whole lot better. Just shrink that just so I have a little bit more room. So we're looking here, collecting like terms. Okay, now we gotta solve. So in doing my AC method, I realize 7 times 9 is 63, and hey, those two numbers add up to 16 already. All right. So somewhat exhausting, but we got there. We got solutions of 1 over 7 and 1. Now again, in working with rational expressions, I want to check to make sure that my original equation is defined at my solution values. And I see that right here, 2x minus 2, if I plug 1 into that expression, I'm getting 0, which means that would cause division by 0. So this is extraneous, which means actually the solution is just 1 over 7. And the original equation is defined at 1 over 7. So it's all good there. All right, now to put a little bit of a different spin on it, we're looking at the function f of x is equal to 2x minus 6 over x squared minus 8x plus 15. Cool. First, we want to find the domain of x. Remember, for rational functions, that just boils down to figuring out where the denominator is equal to 0. And we may as well factor this guy, just so we know. So upstairs, we have a common factor of 2. And we're left with 2 times x minus 3 over x minus 3 times x minus 5. Now, the domain has restrictions when the denominator is equal to 0. So that would be at x equals 3 and x equals 5. The quote-unquote canceling or dividing out these x minus 3's, like you probably feel a strong urge to do, is only valid when x is not equal to 3. So the original function is not defined at x equals 3. even when we simplify, that doesn't change the domain of the original function that was undefined at 3. So the domain is everything less than 3, everything between 3 and 5, everything greater than 5. All right, for part B, we want to find the values of x in which f of x is equal to 1. And what we're going to do is take 2 over x minus 5, and we're going to set it equal to 1. And if I multiply both sides by x minus 5, I'll get 2 equals x minus 5, or 7 equals x. And that's okay. The original function is defined at 7. The original function's only not defined at 3 and 5, so 7 is okay. Now we want to know for part C the points on the graph in which f of x is equal to 1. Well, so this is really just putting together the information we already have. We know that the x-coordinate where f of x is equal to 1 is 7. Automatically, the y-coordinate's 1 because that's how we solved for that value. And yeah, solving rational equations. Next up, we are going to look at a few of the applications of rational equations. It's it's been a minute since we've done some word problems, so let's turn our attention to that for a little while.